Okay, address translation, or I should rather say memory address translation in operating systems. There is also a topic of address translation in networking. That has nothing to do with this one. Here it is about memory address translation. So first of all, what is address translation and what do we need it for? So imagine you have a very big folder with, let's say, 1,000 pages or whatever. This is your folder. Here you have, yeah, a high number of pages inside. And when you want to access a page of that, you don't want to read the heading of every single page. So you will need some kind of index that tells you, okay, if you want this and that page, you will find it on, or this and that content rather, you will find it on a certain page. So you would have an index where you have the content, like in a table, like this roundabout. You have your content, whatever it is. Then you have a page, whatever it is. And then additionally, because a page can be very long and have several contents, you would have a page offset, which you can imagine as some kind of maybe the line on the page. So when this is your page inside your folder, here, one example page, you would have your page number here, and then you would have various lines, and maybe even inside the line you would have different words, and then that would be your page offset. So these are the informations that you have in this table, right? So now if you know you want to read about a special topic, you have this table. This tells you, okay, go to this page, and on this page go to this part of the page, which is told to you by the page offset. Now, so far so good, but here no translation is happening, right? So let's first of all bring this analogy to the computer. So in the computer, the folder would be your memory, where you have the content saved that you need to run your program. And the thing that actually wants to access your memory is the program, right? You wouldn't do that yourself, but you execute a program, and then the program is looking for the data that it needs to run in the memory. Now, your memory, as I explained in the last video, if you haven't seen that about page replacement, you can see that on my channel. But you have different pages in your memory. So your memory is divided into blocks, if you want so. These blocks are also called pages, which is why this analogy works very well. And then inside the pages, so imagine this being the folder, then every square being a page, and then in these pages you have smaller blocks, if you want so, which are resembled by a page offset or linked to by your page offset. So your program wants to access something in here. Now the problem why we need address translation is that you have a virtual address and you have a physical address that are not the same. Now the question is, of course, why are they not the same? And the reason for that is, so the virtual address is what your program works with, and the physical address is what is actually the physical thing on your computer, the real address. And they cannot be the same because the program does not know how your computer is managing its memory. So you might have various programs running. Let's say you have Photoshop running, and then you have Spotify running, and all that at the same time, right? And you have your memory here. And they all want to access your memory, but they don't know of each other. And that is, for example, done, first of all, to allow the computer to manage its resources more efficiently, but also to add an additional layer of security. So that if one program might be malware, for example, it does not have total access to your whole memory and to other programs and so on. So what is done is that every program thinks it is the only one and it has access to all of the memory. So Photoshop might say, okay, I want memory from let's say page 1, page offset 1, because for Photoshop thinks it is the only running program, and from this subjective view it owns page 1 and page offset, so line 1 if you want, so on the first page. What it doesn't know is that actually page 1 and page offset 1 are in reality page 5000 and maybe still page offset 1, because it owns the whole page, for example. Because before, the pages are owned by Spotify or whatever you have running, but without Photoshop knowing. And that is why you need address translation, so that you have on the one side you have the subjective address, if you want, so that the program wants, but then in reality that is a whole different address because the program does not know what else is going on in the computer. I hope that makes somewhat sense. So to make that work, you actually don't only need this table here, but you need an additional table that is in between that step. So Photoshop has its table where it knows, okay, I want this content is on this page with this page offset, but this is the virtual address that Photoshop knows of. So it tries to enter this virtual address, and then there is a table in between that translates this virtual address into a physical address. This is happen inside of the MMU, which is an actual physical part of the computer, which is the memory management unit. So this table is calculated in here. So you have your process, which is nothing else than a program in execution. This requests resources that goes through the MMU, which translates that request to make sure it goes to the right address. And then you have your memory where the data is requested and then sent back to the process. So this is basically what's happening. I hope I could make the process somewhat understandable and clear. And next we are going to look into an example for that. Okay, so to make this less intimidating, let's start with a very simple example. And the task is translate the virtual address to the corresponding physical address. And the virtual address is just the same as the logical address. These are synonyms, they mean the same thing. So if you have a different term, don't be confused by that. And yeah, we want to translate that into the physical address. Now we have different information given. We have the page size, we have the word size, we have of course the virtual address that we have to translate, and we have a page table. So what does all that tell us? So the page size in bytes would just be how big our whole page in bytes or in bits therefore is. Now the word size is what I explained earlier as the smallest part of a page where the exact page offset links to. So every page offset value or every possible page offset value refers to one specific point on the page, and that is exactly one word. So the word is the smallest unit, the smallest memory unit of a page, if you want so. Okay, so what can we do with that? If we have a page size that is 16 bytes big, and we have a word size where every word has 1 byte, that means that we have 16 words per page, right? Which also means we have 16 different possible addresses. Or if we have, for example, a page size of 256 bytes and we have a word size of 2 bytes, that would mean we have 128 words per page and therefore 128 different possible locations. And that is important to know because the virtual address consists of two different things. And the one thing is, as I mentioned earlier, the page number, and the other thing is the page offset, right? So these are the two things that make up the virtual address. The page offset actually stays the same in the physical address as it is in the virtual address. This doesn't change. So why do we need this information, how many values for the page offset there are? Well, we have to translate the page number, which we find in the page table, but how do we know what part of the virtual address is the page number? So in this example, as you know, it consists of two parts. It is easy to figure out which part is which, because the 0x has no meaning. That just indicates that we have the address in hexadecimal, but that doesn't give us any further information. So we know AB is the actual address, and therefore it is very obvious what the page number and the page offset is if you know the order. So the page number is the left thing, the page offset the right thing. But now imagine that a virtual address usually is much longer. So you don't know, let's say you have 16 digits. That does not mean that the leftmost 8 digits are the page number. It could also be that you only have 4 left digits for the page number and the rest of the digits are the page offset. That depends on your page and word size. So, but this is a very simple example, but we will just pretend that this is a real life scenario and go through the steps, and then we can follow up with a more realistic scenario. Okay, so now we want to know what part of this is the page number that we can look up in our table. To do that, we need to know how many words and therefore addresses per site we have, per page. So in this case, we know we have 16 addresses per page, and we know this is a hexadecimal representation. So how many digits do we need in hexadecimal to represent 16 different values? There would be 1, right? Because hexadecimal goes from 0 to 15 in one digit, and as in one digit, and as 0 is the first value, that gives us 16 values. So if you want to represent 16 values in hexadecimal, you need 1 digit. So we know that the rightmost digit, this one here, is the page offset. That does not change, but now we know that everything that's not the page offset is the page number, and therefore we can simply read that the page number is A. Again, in this example that might seem very obvious, but it is a very simple example. Now what we do is we look up our page number in the page table to find the according frame. So the page would be the logical address, and the page frame would, the frame number would refer to the physical address. Now we have the page table in decimal, so we have to convert that first, and A in hexadecimal is 10 in decimal, right? So we look for page 10, which is here, and we see that this refers to frame 14. So our frame number in the physical address is 14. This is already part of our solution, but now we have to write that back into hexadecimal. So this stays the same. 0x because it is hexadecimal representation. Then we put in 14. 14 in decimal refers to E in hexadecimal. So we write E for the frame number, and as mentioned earlier, the frame offset or the page offset stays exactly the same in the physical as in the logical address. So this is still B, and then we end up with the address 0xEB. So let's recap what we did. We have our address, and we have to find out what part of this address is the page number and what part is the page offset. We can't read out the page number, but we can figure out how long the page offset is, and we know it is the rightmost thing. We find out how long the page offset is by viewing how many different addresses you have per page and how many digits you need to represent that. So as we have a page size of 16 bytes and a word size of 1 byte, that means that we have 16 different addresses per page. And in hexadecimal, to represent 16 different possibilities, we need 1 digit. So would we use a binary address? We would of course need 4 digits, because we have 1, 2, 4, 8, and all that together is 15 plus 0. So we would need 4 digits to represent that, but in hexadecimal it is 1 digit. Therefore we know that the rightmost digit of the virtual address is the page offset, which means that the rest of the address is the page number. Here we only have 2 digits, so only A can be our page number. Then we translate our page number from hexadecimal into decimal, so we can find it in the page table. Here position 10, and we see it links to frame 14. Then we just have to convert 14 back to hexadecimal, and we put it in the place where we had our page number before. The rest doesn't change, and therefore we end up with 0xEB for the physical address if we have the virtual address 0xAB. But keep that in mind, that always depends on the page table. So put very simply, you basically just extract the page number from the virtual address. Then you look into the table, and then you put the frame number in place of the page number from before. That's it. Okay, let's do another example with slightly bigger numbers. Still, these are not realistic numbers, but they're just one step in the right direction. So we have a page size of 1024 bytes. We have a word size of 4 bytes. The virtual address 0xEF38A1B, and we have a page table given again. So what do we do first? We want to figure out what part of the virtual address is the page offset, because then we know that the rest is the page number that we actually have to find in the page table. To do that, we have to know how many digits we need to represent all addresses in that given page. And for that, we have to know how many addresses there are. So we take the page size and divide it by the word size, because that gives us the number of words. So 1024 divided by 4 are 256. This is not supposed to be a division symbol, so we have 256 words on that page, and therefore we have to represent 256 different locations. As 0 is the first location, the highest number we have to represent is 255 in decimal, which is FF in hexadecimal. And that means to represent these 256 addresses, we need 2 digits. So if we have a look at our address again, 0xEF38A1B, I'm going to copy it here to not mess it up too much up here. So we know this part is our page offset, the rightmost 2 digits, which means that the leftmost 5 digits are our page number, which is the part that we need to translate or to find in the table. Now the table again is in decimal, so we have to convert that into decimal. As this is not the main topic of this video, I prepared that. So EF38A in hexadecimal is 979.850 in decimal. So 979,850. Now, this is of course just part of the page table, but somewhere in the page table we will then find this page, which refers to the frame 420420. So this would be the frame that we want to have in our physical address. But we have to convert that back into decimal again. Into hexadecimal, sorry. From decimal into hexadecimal. And I prepared that as well. That would be 66A44 in hexadecimal. So, as mentioned before, the rest of the address, like the 0x to indicate that we are in hexadecimal, and the 1b stay the same. We just have to replace the EF38A with our new address. So that we end up with a physical address 0x66A441B. And that is it. That is how you translate from a virtual address to a physical address. And keep in mind, there can always be tasks like how many bits do you need, or how many bits do you have in this virtual address also. But these are all just subtasks of this one. This is all included in this one. So if the question is how many bits does the page offset take in the virtual address, you do the same process as before, but then when you know you have 2 hexadecimal digits, of course you have to convert again how many bits do you need for that. So you would have to know how many bits do you need to represent the number 256, and so on and so forth. So there are many different tasks to make out of that, but if you understand this process, you can pretty much extract every subtask from that, and you will be fine.